Dane Flannery from Galway. He's going to tell us about classifying finite linear groups of prime degree.
Okay, thank you, and thanks very much to the organisers. So this talk is a bit of a trip down memory lane. It's a long-running project, very long-running project, joint work with Zolt and acskai and Eamonn O, Brien that's recently achieved some sort of resolution. In fact, a lot of the later results I'll talk about are based on work that Zoltan did in his PhD thesis with Lotzi Kovac. So the imprint of Lotzi on the work I'm going to talk about is quite profound. But anyway, so our basic problem, classifying linear groups, it's a venerable problem, enduring interest. Results go back 150 years to the beginning of group theory itself. What I need to do at the beginning is be clear about what we mean by the word classify, because it's been interpreted variously, at least within linear group theory. So a classification for us is a classification in GL that is complete, irredundant, and explicit. That is, for the specified degree n, field f, and whatever type of group you're interested in, finite, irreducible, primitive, solvable, nilpotent, whatever, produce a list of groups of this kind within GL such that any group of this kind is GL conjugate to one and only one group on your list. Moreover, return your groups explicitly as generating sets of matrices. So this is a big ask, and I guess, you know, it's the most comprehensive kind of classification you could want. So there have been many classifications that fall under this or looser headings. You know, special degrees have attracted the most attention. Small, here small means probably less than 10. Prime degree that's the product of two primes. Prime degree in particular has some nice advantages. For example, there's only one way that an irreducible linear group of prime degree can be imprimitive. That is, its imprimitivity system is comprised of one-dimensional subspaces. So it can be conjugated to a group of monomial matrices. Another reason for the popularity of prime degree is that prime degree classifications can be ingredients for classifications in composite degrees. Okay, so as far as the field goes, well, classifying finite linear groups over the complex numbers, this has been studied from the very beginning. Results in degree 2 obtained by Klein. But finite fields are also of interest. There are many applications of classifications of irreducible linear groups over finite fields in computational group theory. Okay, so anyway, all right, because of the the nature of the classification we're asking for, even for very stringent restrictions on the parameters of the problem, you're almost immediately faced with a mass of details about the groups. So it makes sense to push the solution by hand as far as you can go or stand, and then turn the rest of the work over to the computer, get the computer to organize all of this detail. The other important thing, of course, is that once you've got the classification implemented, you can test it, you can check it for correctness. And we all know, if we've done classifications, how easy it is to make mistakes at the first go round. Yeah, so that's really, you know, the end aim, to have the working software, have the classification in the computer implemented, ready for people to play around with the groups. Now, our lists are infinite. This is the other thing. So there's a standard dodge that has been popular to reduce the problem to SL and then ignore the imprimitive groups, just classify finite primitive groups. And the example here to point to is that in SLNC there are only finitely many finite primitive groups up to conjugacy as a consequence of this theorem of Jordan's that, yeah, I won't go into it, but yeah, so our classifications are infinite. So there's a question about how to organise that, you know, in a manageable way. Another traditional route was just to classify maximal subgroups within the class. Of course, this makes sense as long as every group that you're interested in is contained in a maximal. But this is the problem that I'm going to talk about, that we have a good solution to, an effective solution, for an arbitrary prime, P, classify, in our sense, completely, irredundantly and explicitly, all of the finite, irreducible, monomial subgroups of GLPF. And as I say, we have a good working solution for infinitely many P for the complex numbers, with an important caveat that I'm going to talk more about towards the end of the presentation. We can make this classification work for other fields of characteristic zero, but we don't really lose much by just sticking to the complex numbers throughout. Okay. A small slice of history of classifying finite linear groups. So, okay, results go back to antiquity. In the late 60s, early 70s, there was a renewed interest in classifying finite primitive linear groups over the complex numbers, going up to degree 10. But it's this 1976 paper by Sam Conlon that I want to point to as setting a new standard, our kind of standard in linear group classification. So Conlon classified the finite P groups with an abelian maximal subgroup and cyclic centre. Fairly restricted class. Turns out that this is equivalent to classifying up to conjugacy the finite P subgroups of GLPC. So this paper, you know, set the new standard, inspired people working later on under the guidance of Lotze, and what I'm talking about is a solution to a central problem that's part of this school. One final important citation I have to make, and that's to a paper by John Dixon and Alexander Zaleski. They consider the same problem, classifying finite, irreducible, monomial groups of prime degree over the complex numbers with important differences. They are concerned only with non-solvable groups and restricted to SL. Now, there's quite a difference between classifying in SL and classifying in GL. That's a paraphrase of a comment by Walter Fite. He eventually became convinced of that point of view as well. But okay, so let's get down to some basics, set up some basic terms and terminology. So my notation for the group of all monomial matrices, n by n over the field F. So this contains the group diagonal, full diagonal group of all diagonal matrices, splits over it by the group of n by n permutation matrices, which we identify with the symmetric group of degree n. Okay. So any monomial group, that is subgroup of MNF, is an extension of its diagonal subgroup by its permutation part. That is the image of G under the natural surjection of MNF onto the symmetric group. All right, so we're constructing extensions of diagonal subgroups by permutation groups. The diagonal subgroup is a module for the permutation part under conjugation. Okay, so one thing I guess you might notice straight away is that if your group, your monomial group, is irreducible, then its permutation part has to be transitive. Of course, not vice versa. It's acting transitively on a basis of the underlying vector space. So there's a classification problem, right at the beginning, classifying transitive permutation groups of the given degree. All right, and another important initial observation, this affects the format of the groups that we list in our classification. If your monomial group is finite and has a transitive permutation part, then you can conjugate it to a group of monomial matrices whose non-zero entries are roots of unity. That is, you can slightly restrict your classification to subgroups of this M tilde, where we replace the full diagonal group with just its torsion subgroup, D. Okay, so this basic discussion suggests the following general strategy for solving the classification problem. And we'll stick to degree P, although this strategy applies in general. So step one, of course, classify all of the transitive permutation groups of degree P. That problem at least has a full hermetic solution. Classify them up to conjugacy in the symmetric group. The next step is to solve the submodule listing problem. List all of the candidates for the diagonal subgroups of the groups in your final classification. That is, all of the T submodules, finite T submodules of D for each T from step one. Then solve your group extension problems in M tilde for each T from step one and A from step two. And you only want to keep the irreducible groups, so can we test irreducibility? And finally, now along the way you'll have been cutting things down using the fact that you're only listing or only interested in things up to conjugacy. So the final step is to make sure that you delete any remaining redundancy. So that's the conjugacy problem. Okay, so there is quite a bit of work, as you can imagine, behind each of these single sentences. Most of the complication, the taxonomic difficulty, arises in step two, listing all of these submodules, especially for solvable groups, solvable T. But let's deal with this irreducibility issue first. This is surprisingly easy to decide. Almost always, irreducibility is equivalent to the diagonal subgroup being non-scalar, at least for the solvable groups, not for the non-solvable groups. It fails as soon as it can, the converse, but it's not going to cause us much trouble. So irreducibility, as I say, almost always. Just get rid of the scalar diagonal subgroups. That's very straightforward. So let's review the solution to step one. So classifying transitive permutation groups of prime degree, you would guess that this has been studied for a long time, and it has. There's a nice survey article by Peter Neumann that gives all of the information on the next two slides. Okay, so pick a favourite P cycle, S, this notation for the rest of the talk, a normalising element T, order P minus 1. Okay, so a transitive subgroup of the symmetric group T. We can assume it contains S without loss of generality. Remember, we're only classifying things up to conjugacy. So here's a fundamental theorem. T has a unique, simple, normal subgroup that's transitive. Call that U. The normalizer of U, mod U, is cyclic of order dividing P minus 1. So straight away we can write down a description of the solvable permutation, transitive permutation groups of prime degree. Okay? The metacyclic. So the non-solvable groups are summarized in the following table. The first line is these are compulsory. They're there for every prime degree. Last two lines, some exceptional cases in degrees 11 and 23. It's this second row, this projective family that causes us the most angst later on. So they're present for every P of that form, Q to the D minus 1 on Q minus 1. Okay, so here's a theorem. I'm not sure how well known it is, but it's very useful for us. It uses the last column of the table. So transitive subgroups of sim P are isomorphic if and only if they're conjugate. Anyone heard that before? But that impinges on our conjugacy problem straight away. So if we have monomial groups that are conjugate or even isomorphic, then okay, in transitive permutation part, then their permutation parts must be the same. So what this means is that we can do everything for each isomorphism type of T, and then take the union of the sublists that we get at the end of that process, and we won't have any overlap. Okay? No conjugacy between different sublists. So sticking with the conjugacy question, so the main thing to look at here is whether conjugation maps diagonal subgroup onto diagonal subgroup. If it doesn't, then your monomial group must be solvable. That's the only, right? That's the only way that this can happen. And if diagonal subgroup does map to diagonal subgroup, at least for the irreducible monomial groups, then the conjugating matrix has to be monomial itself. Better still, if the field is algebraically closed, it's in M tilde, right? A monomial matrix with non-zero entries, roots of unity. So they're the highlights of the conjugacy problem. But so the first thing to do there is to sort out the conjugacy classes in M tilde. And then, you know, there'll be a small number of exceptions of conjugacy by non-monomial matrices. All right. So, done step 1. Step 2, the submodule listing problem, and as I said earlier, this is where all of the overwhelming detail arises. So we have to start by working out the S modules, right? Remember S, we're assuming that S is in every T. So we're going to get here all of the modules that we're ever going to be interested in. Okay, so the full diagonal group is a central product. X times Z. Z is the full scalar group. X is the intersection of D with SL. Right? We're algebraically closed, so that is possible, this decomposition. The intersection is the scalar of order P. So what we're going to do is describe the submodule structure for each of these factors, Z and X, and then combine that information to work out all of the submodules of the central product, or the direct product once we factor out by the scalar of order P. So nothing to say about Z. For x, we're going to split the discussion up into p groups and p dash groups. So xp, the CLO p subgroup of x, is uniserial as an S module, has a unique submodule at each p power order. And we can write down module generators for those. So that's enough information to combine with the following theorem, which again maybe you've seen before, for determining all submodules of the direct sum or direct product of two modules. It's this Gauss-Remak theorem, so I'll just blurt it out. So anyway, the point of this theorem is that the set of submodules of the direct product of two modules is in one-to-one correspondence with a set of isomorphisms, module isomorphisms, between sections of the direct summands. And we've got all of that information for the p groups. So we've got all of the submodules, S submodules, of D of p power order, exactly by this method. And you can see that the theorem tells us how to write down module generating sets. So we get all of our explicit information as required. Right, so the submodules of Q power order, okay, well, the picture is quite different. Now the diagonal group, CLOQ subgroup, DQ, is a direct product. To describe the submodule structure of XQ, we work over just for convenience, the ring of Q-adics, and isolate this polynomial f, which you might notice the kernel of f of s on D is exactly x, the SL part of D. Okay, so this polynomial is crucial. Just a bit more notation. V, p minus 1 on D, where D is the multiplicative order of Q mod P. So here's how we begin. Reduce F mod Q. Factorize F over the finite field, and then lift those irreducible factors over the finite field to ZQ. This gives you the irreducible factorization of F over the Q-adics. Define XQR to be the subgroup of XQ annihilated by FR of S. So this is a module, a ZQS module, and these are the factors in the direct sum decomposition of XQ. So that's a module decomposition. And each of the module factors we know, or we can work out, have worked out, its submodule structure. They're all uniserial. The only submodules they have are the ones that they must have, these omega n's. And, okay, how do we work out submodule generators? Well, this is buried in the proof of the lemma on the previous page. It's essentially Hensel lifting, so that's not really a problem again. And now we have all of the information to assemble module generating sets for DQ. And in fact, they're all direct products because there are no isomorphisms, module isomorphisms, between non-identity sections of these direct module factors. And that's basically it for the submodule listing problem. So I can go straight on and talk about the extension problem for the solvable monomial groups, starting with extending by the cycle of order P. So here is the very compact description of all possible extensions that we're going to be interested in. There's nothing deep behind this lemma. It's basic matrix manipulations. So there's two possibilities. Either the extension splits over the diagonal subgroup, or at worst you're adjoining a scalar, a scalar of p power order that's determined by the single group relation in the quotient. So this much was observed by Conlon. Okay, irreducibility, well, the groups are solvable, so this is equivalent to the diagonal subgroup being non-scalar. So that's out of the way. Conjugacy, as I mentioned earlier, the thing to look for first is whether the diagonal subgroup is mapped to the diagonal subgroup in the other group. So groups with a unique abelian normal subgroup with quotient T, these can be conjugate only by monomial matrices. Otherwise, the group has a scalar subgroup of index p squared, so it's nilpotent of class 2. There are only 2 conjugacy classes at each order, and conjugacy is affected by a van der Waals matrix. Don't know why that's interesting, but anyway, that's what we used. Okay, so that deals with permutation part cyclic of order p. The other remaining cases for the solvable monomial groups don't present any new phenomena or are, so that's where we'll draw the discussion to a close for the solvable monomial groups. They're all done, okay, so in any prime degree. Moving on to the non-solvable permutation part. So I'll begin here with some general purpose results that apply for any prime degree, and so now we can assume that p is bigger than 3. So let T be any non-solvable transitive subgroup of sim p. We'll assume, as always, that we've got our canonical p cycle in T, and pi is the set of all primes dividing the order of T other than p. Q is any prime. So I'll mention 2 general results for the submodule listing problem first. So submodules that are p groups, these are, for T, are exactly modules for the full symmetric group. And that cuts things down amazingly, at least for the p groups. For submodules that are q groups, for q not equal to p, xq is indecomposable as a T module, and that has one nice corollary. If q doesn't divide the order of T, then the familiar result, yet again, xq is uniserial. The only submodules that it has are these omega n's. That's it really. I mean, in general, the submodule listing problem for arbitrary p non-solvable permutation part T is open, and I'll say more about that in a few more slides. The extension problem for the non-solvable groups. Okay, the way we proceed here is to successively split off more and more of the diagonal subgroup. And that will focus the extension problem in a much smaller monomial overgroup. It's easier to handle. The first thing we can do is get rid of all of the primes that don't divide the order of T, as well as P. We can get rid of P as well. So what this initial theorem says, valid for any P, that we can get down to this hub group in TD pi. We can split off the pi part of the diagonal subgroup of our monomial group. And the other interesting thing, useful thing, is that we can retain our p cycle inside the group. It's inside the permutation part, but we can actually get it inside the group. So that doesn't figure in the extension problem either, really. Okay. So we can go further still. As I say, this basic idea of splitting off more and more of the diagonal subgroup until we get down, you know, to really to a core. So theorem 1 here, numbered for later reference. So this picks up where the previous theorem left off. So let's suppose we do have a hub group. G, our monomial group is in TD pi. And as long as these conditions hold, so d pi has a direct decomposition as modules, B cross C, where B satisfies this cohomological condition on the first cohomology group. In that event, we can split off the B part of the diagonal subgroup, okay, and still retain our favourite p-cycle inside. So we get down to solving the extension problem in TC. Right? So we want B to be as big as possible, obviously. So theorem 1 here, we apply together with lemma 2, which I guess shows that the quotient that we have in theorem 1 here, this is often, as a module, structure is independent of G. Here's the full statement. Okay, so this is what we need. Zeta, the set of all primes in Q, such that omega 1 xq is irreducible as a T module. So take the product of those xq's and throw in any number of zq's. So that T module B, if you factor out by any finite submodule, it's isomorphic to B. Okay? Right, so a side comment. The first degree at which the previous 2 results fail to be of any help is degree 7. And this is where we meet one of these notorious projective permutation parts. So special ad hoc arguments we needed, Zoltan came up with for degree 7 in this case of permutation part. So theorem 1 requires cohomology calculations, and there's nothing new here either. It's standard, so I just quote the Ekman-Shapiro lemma. Our co-induced modules come up from scalars, so that also is particularly helpful. Right. So how much time do I have left? Oh, great, good. So what I'll do next is just illustrate for one case of non-solvable T the application of the results on the previous 2 slides to solve the extension problem. So here we'll assume that the permutation part is as big as it can be, the full symmetric group. It turns out to be the easiest case. So here are the extensions that we get. So yet again, either the monomial group splits over its diagonal subgroup, Kr is the other generator that you need for the quotient, or we're adjoining a scalar to the other generator. And that scalar has 2 power order, and again determined by a relation in the quotient. All right, so here's the sketch proof. So remember, we can immediately go down to a hub group, G and d pi t. So yeah, S is always there. So let's decompose d pi as B cross C, where C is Z2. The reason we do that is because in this case, for all Q in pi, omega 1 xq is irreducible as a T module, as a sim P module. So lemma 2 implies that this quotient module is isomorphic to B. We do the cohomology calculation. First cohomology of T with coefficients in B and factors 0. There's a bit hidden there, but everything is in place now for theorem 1. Theorem 1 implies that we go down to solving the extension problem in TC, that is TZ2. And so that's why the scalar has 2 power order. And that's it. Okay, so I think it's time to sum up a bit. So in summary, we've got a complete solution to our classification problem in any degree for all solvable groups, for all groups whose permutation part contains the alternating group, and in degrees 7 and 11. There are exceptions there you might remember to deal with. Now, in fact, Zolt sketched out solutions for all degrees up to 23, but we've only implemented the classifications up to degree 11. But I think it's safe to say that prime degrees less than or equal to 23 are more or less done. Now, of course, we cover infinitely many degrees, but there are infinitely many gaps, and the gaps come from the projective family as the permutation part. We don't, in the first instance, have a solution to the submodule listing problem. But some patterns have been noticed. So I'm just going to flash up 3 conjectures here, which might or might not ring a bell with things that were said earlier. If we could resolve these conjectures, that would go a long way to closing this initial gap for projected permutation part. But if we're going to find a counterexample, we won't get it until very high degree, at least for conjecture 1. Right, this is the first degree at which the normalizer is different from T. Yeah, so, okay, just a few concluding comments on the implementation. Not that much to say here, really, but okay, we return the groups as generating sets of matrices, and the field that we return them over is essentially determined by the user, specifying an order bound on the groups that you want. So we choose a suitable cyclotomic field to represent the groups, and apparently there's a bottleneck related to the representation of the field. Eamonn can say more about that, but more importantly, testing correctness. So there are some obvious things that we can do, as in this lemma here, to make independent checks that our lists really are complete and are irredundant. So the test furnished by this lemma is restricted to solvable groups, and again, that's not a theoretical. The reason for that isn't theoretical. It's system dependent. So the non-solvable groups we're able to reconcile as far as possible with the partial information in the lists of Dixon and Zaleski. So we made some mistakes, actually. They were right in a few instances. So, yeah. Jolly good. Okay, one final comment, and this is to justify the omission of a word in the title of this talk. So in the very small degrees 2 and 3, in fact, we have proved or compiled, cobbled together from classical sources and other papers, classification of all finite irreducible subgroups, GL2C and GL3C, not just the monomials, the primitives as well. So, these classifications, partially bits and pieces here and there, but it's there and working now for general use. Okay, so I'll stop there. Yeah, exactly, yeah. But I mean the theoretical classifications. Yeah. No. Yeah. Yes, excellent point. In his survey, it wasn't known whether the table was complete. Is that right? Oh God, I'm going to be forever getting back to it. But I think that's the case. That at the time he published his survey, which was in the mid to late 70s, it wasn't known whether the table was complete. Yes. Yeah.